In this section, we will talk about electron configuration in modern atomic theory. Uh, Atomic structure is how electrons are distributed among an atom's cells, subcells, and orbitals. Understanding electron configuration helps us explain the chemical reactivity, bonding, and periodic trend of elements. We also looked at some example of electron configuration using a previous Bohr model in previous video. Now we will create this electron configuration using a modern quantum mechanical uh, model. Uh, we talked about this filling rule before, where we explain how this filling rule will this quantum four quantum number uh, defines the exact location of an electron within an orbital. And we talked about this different principle of filling this electrons, and the first one is Aufbau principle. This is the Aufbau principle is basically a German for building up. And we also talk about how how electrons are inherently lazy, and they feel the lowest energy first before moving to a higher energy level. For example, 1s subcell will fill before 2s, and 2s will fill before 2p. This process minimizes the total energy of the atom. And then we have a Pauli exclusion principle, and it states that no two electrons in an atom can have the exact same set of four quantum numbers, and it also mentions that each orbital within a subcell holds a maximum of two electrons, and they must have opposite spin. So if one is spinning down, the other electron within the same orbital should spin up. And then we have Horn's rule. When electrons fill degenerate orbitals, or meaning orbitals of the same energy, such as the three orbitals we said, such as 3p orbitals. Oh, if you remember, we said that S subcell has only one suborbit, only one orbital. P has three orbitals. P subcell has three orbitals. D has five. F subcell has seven orbitals. So for same for a subcell that has multiple orbitals called degenerate orbital, the electrons fill one per orbital first, and with the parallel spin, meaning the same spin, and then they will pair up once they fill all three orbitals. And this process of parallel spin minimizes electron to electron repulsion on an atom. And if we go back to previous slide, previous video, we should also mention that Since one orbital can have two electrons, and say the subshell S has only one orbital, that means uh, subshell S can have two electrons, and this can have 6 electrons, and this has 10 electrons, and F subshell can have 14 electrons. When writing electron configuration, we follow a logical step-by-step method. It's pretty straightforward method, but we have to follow a logical step-by-step procedure. So the first step is to count the total number of electrons, and we can do that. We can identify the number of electrons by looking at the periodic table. For example, carbon has an atomic number of 6, so carbon has 6 electrons. Aluminum has an atomic number of 13, and if you look at the periodic table, aluminum has 13 electrons. uh, After that, you will look at the energy level of the element or the atom within the uh, periodic table. And as we know, each row of a periodic table represents the energy level. And for example, if you are looking at carbon has electrons in n equals to 1 and n equals to 2 energy level. So basically K and L. So the first energy level has hydrogen and helium, and then carbon is somewhere here in second period. And you should also know this energy level are also represented by K, L, M, and so on. So you shouldn't be confused if you see KLM instead of n equals to 1, 2, 3, and so on. And the third step is to identify the subshell for each energy level. And for energy level 1, there is only one subshell. For energy level 2, there are two subcells, S as well as P. For energy level 3, we have S, P, and D subcell. For 3, we have S, P, and D. And then we should also remember the capacity of each subcell. And we just talked about this in the previous slide, that one S subcell can only hold up to 2 electrons, P subcell can hold up to 6 electrons, D subcell can hold up to 10 electrons, F can hold 14 electrons, and so on. And for a sub level, the generic flow of this electron configuration is in this form: 1s, 2s, 2p, 3s, 3p, 4s, 4p, and so on. And we can, in order to determine this arrangement, we can look at this diagram here. Here we can see we have a first energy level, and there is only S subcell. Second energy level S and P. Third energy level SPD. Fourth energy level SPDF. Fifth energy level SPDFG, and so on. So if you look at this diagram, you can see this arrow going like this, And if you look at this arrow is moving like this, and the way we determine this electron configuration is following this arrow. If you look at here, this arrow started from a 1s and it moved to 2s, and then it went to 2p. From p it went to 3s. From 3s it goes to 3p. From 3p, instead of going to d, first it goes to 4s, and then from 4s it goes to 4d, from 4d 4p, 5s, and so on. And since we now know the general flow of this electron configuration, all we have to do is find the find the number of electron and divide these electrons within different subcells. And for a reminder, we can also see the different shape of these subcells. One as the S subcell is basically a spherical shape. P subset has 3 orbitals, and the shape of this each orbital looks like a dumbbell, but the orientation will be different for px, py, pz, and so on. And if you are looking at the orbital for in d subcell, we will have a complex shape. Similarly, if you move further, the shape will get more complicated. And let's look at an example. Let's look at an example of oxygen. And if you go back to a periodic table and find the atomic number of oxygen, the atomic number of oxygen is 8. That means we have 8 electrons in oxygen atom. And now we know the general trend of the electron configuration. This is 1s, 2s, 2p. So 1s, 2s, 2p. And we also know S subcell can have a maximum of 2 electrons. P can have maximum of 6 electrons. So the first subcell, first subcell here we have 2. In the first block we have 2. In the second 1s, and the second 2s. S subcell again can have 2 electrons, and then we have P, and so far we have 2 plus 2 is 4 electrons. Now we have 4 electron left, and the maximum electrons that can fit in P subcell is 6. So all 4 electrons can be fit in this subcell. So the overall the electron configuration of oxygen is 1s2, 2s2, or 2p4. Similarly, if we look at an example of calcium, if you go back to a periodic table, the atomic number of calcium is 20, and the number of electron is also 20. Now we know the general flow of this configuration: 1s, 2s, 2p, 3s, 3p, 4s, and so on. First we will just write this configuration: 1s, 2s, 2p, 3s, 3p, 4s, and so on. And then we will start filling these subcells. So 1s is 2, then again this is S, we can have a maximum of 2, and P can have maximum of 6, S can have maximum of 2. So this is 10, 12, and then P can have maximum of 2. 12 plus 6 is 18, and S can have 2. So all together we have 20 electrons. So the electron configuration of calcium will look like this. So if you look at the orbitals in calcium, you will have s block with 1s, 2s. Within first energy level, you will have a spherical orbital. In second energy level, you will have spherical as well as uh, dumbbell orbitals, and so on. And the configuration we just saw here from this diagram can also be achieved from a periodic table. Here we can look here. So if you go from left to right, and this all these blocks, if you look at these green blocks, these are S blocks, and this yellow or orange blocks are P block, and this blue block are D block, and so on. And so what we will do is go from left to right, and then right to left, like this. We will move from left to right, basically go from there, come back, go there, in this flow. So if we were to find this general formation like this, what will it be? First, we will start with 1s here, and then if you go here, this is also the s block, so we will exclude this. And if you go here, and the second is 2s, and from 2s 2p, from 2p we have 3s, and from 3s we have 3p, from 3p 4s, from 4s 3d, from 3d 4p, and so on. So the statement I made before may be confusing, saying we are going this. So we can look at this. So if you are just writing as it is, we are basically going from row to row in this direction. So 1s, this is also s, so only 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 5d, 4d, 5p, and so on. Now let's look at more example. Calcium. We already did that calcium example here, and we can do the same from the periodic table. Calcium is 20, so 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20. So calcium is here. Each block is one element, and the arrangement of element are in increasing order, so we can just count the block. So calcium is here. That means first we will fill 1s, and then it will also fill 2s, it will also fill 2p, and then comes back to 4s, and in the s we have one block, two blocks, so 2 blocks. Similarly, if we look at the chlorine is, so this is 20, 19, 18, 17, so chlorine is there. And if chlorine is here, we can see 1s, and for 1s we have one block, two block, So we have 2, and for our 2s again 1 block, 2 block, 2 box. Then we have 2p, and if you look at p, 1 2 3 4 5 6 6, and again it comes back to 3s, 1 2, so 2, and then 3p, and if you go here 1 2 3 4 5 blocks. So if we count total, this is 6 for 10 plus 7 17 electrons. So this is how we can draw the electron configuration using the quantum mechanical model.